All right, so we start already?
Right. So the next speaker is Daniel Harlow, who will tell us about a theory of the black hole interior.
Hi. First I'd like to thank the organizers. It's great to be here. I'd also like to thank the organizers for having the guts to do this in person. I guess we don't know yet whether it's successful or not, but I hope it is. So here's the longer version of the title, The Black Hole Interior from Non-Isometric Codes Protected by Complexity. So in quantum gravity, we've long expected that space-time is only an emergent notion, which is valid only in certain situations and only in some approximation. This idea goes back a long way. In ADS-CFT, this idea is realized mathematically using this language of quantum error correction, where we say that we have some bulk degrees of freedom, which I've represented by these dots here. And in the simplest version of this, you think of these as describing a code subspace of states, which are the states that don't have black holes in them. And then this set of bulk degrees of freedom are mapped into the boundary degrees of freedom by a holographic map, V, which is an approximate isometry. Okay, I promised my collaborator I would define isometry. So an isometry is a linear map which preserves the inner product. And it only exists if the dimensionality of the target is at least as big as the dimensionality of where you started. Now, this idea can be extended to states with black holes, which is good. Certainly if ADS-CFT makes sense, we want to understand it in all the states, not just the states that don't have black holes. Well, until recently, I would say it was only really understood when the encoding map only acts on degrees of freedom that are outside any of the black holes that you happen to have around. So when that's true, then you can fit it into this same idea of you have an approximate isometric encoding map. Just takes the outside and maps it into the boundary degrees of freedom. Now, it's been understood for some time that you cannot reconstruct, quote, the black hole interior in this way. And so there's a long literature here. I was just at the Verlinde conference, actually, and there was some discussion of should you cite it as 2 times Verlinde or Verlinde squared, but I think Verlinde tensor product, Verlinde is really the right. So today I'm going to present a proposal for how we can reconstruct the black hole interior in the fundamental degrees of freedom with applications to the black hole information problem. So this will be based on a paper which just came out last week with Chris Akers, who's here, Ned Engelhardt, who is there, and then Jeff Pennington and Shreya Vardhan. Shreya is a MIT grad student who's just moving to Stanford right around now. So, okay, let's say we want to have a holographic map for the black hole interior. Well, so we have to say what are the degrees of freedom from the gravitational point of view and what are the fundamental degrees of freedom. So when we think in the gravitational effective field theory, I'm just going to model it as saying we have some left moving degrees of freedom in the interior of the black hole. We have some right moving degrees of freedom, so little l and little r. And then I'm going to couple that to some system out here. The black hole is coupled to some exterior, which we can call either the reservoir or the radiation. So this is the effective field theory picture of what's going on. And then what we would like is some sort of holographic map which maps us from the effective field theory on this Cauchy slice, sometimes called a nice slice, into some fundamental description of what's going on, where we have the black hole microstate degrees of freedom B, and then they're coupled to the stuff that's outside of the black hole, this reservoir or radiation system R. And so I'm going to take the encoding map to have the form of V tensor the identity on R. So R is some auxiliary system, it could be anything. And so the holographic map should not act non-trivially on it. And so the non-trivial part of the holographic map just takes the modes inside the black hole and maps them into the microstate degrees of freedom. Okay, so this is what we want. Okay, and I'm going to adopt some terminology, I'm going to refer to this picture as the effective description, the description that has the emergent space-time in it, and then this picture over here will be the fundamental description. So, for example, in ADS-CFT coupled to a bath, this B would be the holographic CFT, this R would be the bath. Now, the basic problem is that as the black hole evaporates, we're going to eventually reach a situation where there's a lot more degrees of freedom in the interior than there are degrees of freedom in the microstates, because you just get more and more of these modes as the black hole gets older. But once you're in this regime, this is not compatible with V being an isometry, because for an isometry, you have to go from a smaller Hilbert space into a bigger Hilbert space, or at least they have to have the same size. So in particular, if we want to have a linear holographic map, as we will, then there's going to have to be a large number of what I will call null states, which are states that are annihilated by the holographic map V. And so the idea that there should be some large number of states in the effective description which are somehow invalid or annihilated by the map or something like this goes back a long way, and here are some of the references of people who have said this in various ways. Now, it sounds dangerous to say that there are a lot of states in the Hilbert space of effective field theory which are somehow invalid, or which are somehow annihilated by the holographic map. Sounds like we might have noticed that already. And I'll deal with that in a sec, but let me first say that there's also a benefit from having V not be an isometry. The benefit is that if I take some state, here a mixed state, in the effective description, I push it through the holographic map by conjugating it with this V tensor the identity, and then I trace out the black hole so that I'm just left with the state of the radiation. It's actually not true that the state of the radiation I get after pushing this through the map is the same as the state of the radiation that I had before I pushed it through the map. So if V were an isometry, then this equation would be true. Okay, but because V doesn't have to be maybe an isometry, this equation doesn't have to be true. And the basic physical reason is because since V is not an isometry, it can teleport information which is in the black hole interior out into the Hawking radiation. And we're going to see that this is the basic mechanism which is behind the recent calculations of the page curve using the quantum extremal surface formula. Okay, here's the basic idea. We're just going to go with it. We're going to say there is indeed a large set of null states in the effective description Hilbert space, inside a black hole, which are annihilated by the holographic map. But in order to not run into just totally obvious contradictions, we're going to demand that this somehow can't be detected by any observer who does not perform an operation of exponential computational complexity. Okay, and Vijay explained complexity earlier this morning, so I'm off the hook for explaining it. Now, okay, those words sound good, right? Okay, I mean, in fact, one could have said those words at any point. What we're really going to do today is we're going to illustrate these words concretely in several models where we're going to show that this really can work. Okay? And so our models will show they have the following features. So first we'll show that this non-isometric encoding map actually preserves the overlaps of all states of sub-exponential complexity. We'll show that in states of sub-exponential complexity, the entropy of the radiation can either be computed directly in the fundamental description from the definition of the entropy, or in the effective description using the quantum extremal surface formula with the same results up to corrections that are exponentially small in the entropy of the black hole. We'll also see that sub-exponential interior observables can be non-linearly but unambiguously reconstructed in the fundamental description in a way that agrees with the effective description, again, up to exponentially small corrections. We're also going to be able to address the black hole information problem more directly. So what we learned from Hawking, or at least what Hawking argued, is that you can't simultaneously have the following three things. You can't have a finite black hole entropy with a state counting interpretation, a unitary black hole S matrix, and effective field theory be valid near/in a black hole anywhere where there's not a large curvature. Okay, that was Hawking's point, is that there's a contradiction if you assume all of these three things. ADF-CFT, of course, shows that 1 and 2 are compatible, but so far in ADS-CFT, I would say 3 is still a work in progress, okay? And I should emphasize that if you can't address 3, you haven't said anything, okay? Because you can't distinguish a black hole from a lump of coal unless you can explain how 3 is happening or to the extent which it's not happening. Okay. Now today I'm going to present a dynamical model of a holographic map which realizes analogs of both 1 and 2, and not quite 3, but instead realizes an analog of 3 star, which says that effective field theory is valid for sub-exponential observables near and inside of black holes. And so thus we'll see that 1, 2, and 3 star are not incompatible, and so within this model I will claim that the information problem is resolved. Let's get started. So our basic model, not the final one, but the one that we understand the best, the easiest to calculate with, works like this. So we have our left moving and right moving interior modes. We have some degrees of freedom that we hold fixed. You can think of those as, short distance modes, modes that are just a little bit outside of the black hole, things like that. We're going to pass them through a unitary transformation, which is drawn from the Haar ensemble. And then coming out of the map, we're going to project onto some fixed state of a bunch of the degrees of freedom P, and then whatever's left, we're going to interpret that as the state in the microstate, within the Hilbert space of the black hole microstates. And then because it's a good idea, as you'll see in a minute, we're going to multiply by this factor of the square root of the dimensionality of the system that we projected on. This V is not necessarily an isometry because of this post-selection on P. Okay, if that wasn't there, then this would be an isometry. Now, I want to emphasize that we are only drawing U once from the Haar ensemble. We are not doing fundamental averaging. I'm not one of those people who thinks that we should be doing fundamental averaging. Nonetheless, we're still going to use averaging over U, but only to learn about its typical features. So we're not going to trust the result of the average unless the fluctuations are small, okay? Okay, so let's just do a few calculations. So I'm not going to say anything about how these calculations are done. Sorry, I only have 25 minutes. So the first thing we can check is that for any 2 states, psi1 and psi2, we can compute the average over U of the overlap between the encoded versions of these states. And those are just exactly the inner product of the states without the encoding. Now, as I just said, to really know what we're talking about, we also have to check the variance, right? Because this could just be true, on average, but not for each particular U. So we can look at the fluctuations, but indeed the fluctuations are also small. So we can compute the difference of the overlap between the encoded states and the unencoded states, and we see that that's exponentially small in the size of the black hole. So in other words, this map, the holographic map, is very likely to approximately preserve the inner product, even though it's not even close to being an isometry if we're in the regime where the interior degrees of freedom are bigger than the microstate degrees of freedom. Because they're just, in this regime there have to be these many null states, but nonetheless these results are still true. Note in particular that the suppression of the fluctuations is exponential in log B, which has avoided the black hole entropy, so this is an exponentially small correction to the inner product. Now you might say, how is this possible? This sounds crazy, I want my money back. We can illustrate it using an even simpler model where we just forget about the left moving modes, just keep the right moving modes in the interior. Here's some complete basis for them. And then we just take our encoding map to be some uniform superposition over a basis of the black hole microstates. And then these are just a bunch of randomly chosen phases. But again, we choose them once. We don't average over them. Okay? And we can just compute the inner product of 2 encoded states, right? We can do V phase on one basis state, V on the other one, and take the inner product. We just get this sum over phases, and if you stare at it for a sec, you see if n equals n prime, the phases cancel, we get 1. If n is not equal to n prime, then we get something that's exponentially small, because this is like a random walk. So we get a square root of b, but then there's a 1 over b here. So we get something exponentially small. So in other words, you can really fit quite a lot of nearly orthogonal states into a Hilbert space. A lot more than the dimensionality would have suggested. Now, so far we saw that the inner product between any 2 particular states is likely to be preserved. In fact, you can ask for a little bit more. You can ask, for any particular U, we're going to be able to argue that, in fact, the inner product is likely preserved up to exponentially small corrections for all states of sub-exponential complexity. So here I mean a state you can prepare, say, from the all-zero state, acting with a quantum circuit whose complexity is sub-exponential, grows slower than any exponential. The proof uses something called measure concentration, which I'm not going to explain, unfortunately, but it's this beautiful theory that tells you things like if you have a reasonably smooth function from the unitary group to the real numbers, then the fluctuations of that function in the Haar measure, the odds that you got something bigger than the average by more than epsilon are exponentially suppressed in the dimensionality of the Hilbert space that the U's act on. Okay. So it's kind of an amazing thing if you think about it. And in particular, if you apply this formula to the problem at hand, then you get some formula like this, which I won't try to explain in detail, but what it says is it says this. It says that, if we maximize over all sub-exponential states, then the difference in the inner product, is probably not going to be bigger than exponentially small, because we've got this double exponential suppression here in the exponent. Okay. Now, let's talk about the QES formula for a sec. So we can introduce Hawking's state. So in the effective description, this is supposed to model Hawking's picture of what's going on that nice Cauchy slice. So we've got some entangled state on the outgoing interior modes in the Hawking radiation. And then I'm going to introduce some reference system L that just keeps track of however we made the black hole, right? Because the left moving modes inside the black hole just tell you what fell into the black hole, right? They tell you how it was made. So this is our model of what's going on in the effective description. So here's a picture of it over here, right? Here's the Hawking entanglement. And then here are these left movers, which are entangled with some reference system I didn't draw. And then if we can encode that like this by passing it through the encoding map, and we get some state capital psi, which lives on L, B, and R, and big R, which just looks like this. All right, now what we really want to do is we want to compute the entropy of this encoded state on the Hawking radiation. So we can do that using this unitary integral technology. We get some formula like this, or in other words, we get some formula like this. So the second Renyi entropy, we'll start there, is the minimum of either the Renyi entropy of the radiation that Hawking would have computed, because this here is just Hawking's state, or it's this thing which is the black hole entropy plus the entropy of the left moving modes. And with a little more work, you can show that the same is true not just for the second Renyi entropy, but for any Renyi entropy, although you have to work a bit harder. In particular, taking n to 1, we see that this formula is true for the von Neumann entropy. And that's great because that's exactly what the QES formula says, right? It says that when you're in this regime where the entropy of the radiation is small, early times, then the entropy should just be what Hawking says, but then at late times you're supposed to include this island, and then the radiation entropy gets purified, but now you've got the entropy of the left movers here, and then you've got the area of the quantum extremal surface, which is this log B, okay? But I want to emphasize that we have not taken the QES formula S input, nor have we derived it from Euclidean gravity and then used it. We've instead obtained it as output from a microscopic calculation of the entropy using this non-isometric code. Let's now say a bit about how to reconstruct the effective description, starting from the fundamental description. So this is an old problem, going back to these papers. The key idea is the following. For any sub-exponential states, psi1 and psi2 in the effective description, and any gamma in this range, with high probability, the Hilbert space norm of the difference of these two states is upper bounded by the Hilbert space norm of their encoded versions plus something that's exponentially small. So what that means is that although this holographic map is highly non-isometric, it's approximately invertible on the set of sub-exponential states, okay? So this ensures that every state in the fundamental description has at most one interpretation in the effective description, thanks. It might have none if it is highly complex. On the other hand, this inverse is not a linear operator since the set of sub-exponential states does not form a subspace. So using this nonlinear inverse, we can reconstruct the quantum mechanics of an interior observer in the fundamental description. Every sub-exponential measurement in the effective description can be turned into a measurement in the fundamental description with the same probabilities and outcomes up to exponentially small corrections. The nonlinearity is reminiscent of Papadodimus and Raju, who had another way of trying to do this, but the invertibility that I just mentioned avoids the ambiguities that arise when you try to do things their way. This reconstruction is compatible with an entanglement wedge reconstriction, and in particular, like Vijay said, at late times you can reconstruct the interior using the radiation alone, and indeed it'll be exponentially complicated. All right. On to the good stuff. So far we have considered the holographic map only on a single time slice. What about dynamics? As time evolves, the various Hilbert space dimensions all change, so we need to introduce time-dependent versions of all of these things. We have a time-dependent holographic map, which takes the left and right movers at time t and maps them to the black hole microstates at time t. We then want to define a discrete time evolution operator, ut. So at time t, actually technically you want to act with ut plus 1 in our conventions, but anyways. And you want this to be equivariant in this sense, or if you like words, that evolving and then encoding is the same as encoding and then evolving, right? So that should be true if you understand how holography works in a dynamical setting. And we'd like to model the full dynamical process that Hawking proposed. We collapse some matter to form a black hole, then we watch it evaporate and see if the process is unitary. So let's start in the fundamental description. We're going to model the collapsing shell as m naught qubits, here they are, these little red ones, whose state we can control, plus n naught minus m naught q dots over here, which are in some fixed state. That's just so that we restrict to states, say, that are formed by a fast collapse or something, so we don't immediately have to think about generic states. We don't want to control all the inputs at once. And then the collapse is implemented by this random unitary u naught here that just kind of eats up everything we threw in and spits out some microstate of the black hole here. At each time t, we then act with a random unitary ut plus 1, and what it does is it absorbs one ingoing qubit, so say this red one here, from the reservoir, because as we evolve, stuff can fall in, right? But then it also spits out two outgoing qubits, these blue ones here, back into the reservoir. And since we're absorbing qubits less fast than we're emitting them, the size of the black hole decreases in time, and you see eventually there will be some last U here beyond which everything is radiation. Okay, so this is the fundamental description of what's going on. It's obvious that it has finite black hole entropy and a unitary X matrix, so it checks boxes 1 and 2. All right. What about box 3? So to understand the interior, we need to define a holographic map V. Here's how it works. So we just take the same dynamics that I just described. Here I've just shown the first few steps. So this is the fundamental description. And then I'm going to do something which at first seems totally trivial, but in fact is also not totally trivial. I'm just going to take these blue lines here, and I'm going to bend them around down like that. Okay? And then that was fun, so then I'm just going to bend them back around and push them up here. But then now if you look at this picture, so this is exactly equal to that, but you see this is some post-selection onto some state. And then here I'm feeding in some entangled state, and I'm going to interpret these lines as the left movers in the interior. This line here is the right movers in the interior, and here's the right movers in the exterior. So then you see what I've got here. If you just look above, like, say, these three lines going up to here, I've got exactly a non-isometric map from little l, little r, and big R to big B and big R. And moreover, you see it accesses the identity on big R, so it's exactly the kind of thing that we were talking about before. We've just reinterpreted the fundamental dynamics as a non-isometric holographic map. This is easily shown to be equivariant. Here's the picture, but I won't explain the picture. Hopefully it looks like a plausible picture to prove that. We can also check that everything we did in the static case carries through. It's an approximate isometry on sub-exponential states. The QES formula is valid for computing entropy. There's an invertible encoding on sub-exponential states in a reconstructible but nonlinear measurement theory. You can also show that the Hayden-Preskel scrambling argument, if you know about that, works. Thanks, and almost done. If you do a little slightly more refined version where the UT are a little bit less random. Okay, I was just going to comment how it's related to the final state proposal. Here's a picture of the final state proposal. I'll just say that the mechanism for how the information gets out is similar. You have this post-selection that teleports through entanglement, but the interpretation is different because in the Horowitz model standard proposal, they modify quantum mechanics in the effective description. There is no fundamental description, and so it's just not holographic. They're just trying to do everything in the bulk, if you like. They also try to interpret the post-selection as being at the singularity, whereas for us, it's in the definition of the holographic map. Their proposal is both nonlinear and acausal. Our measurement theory is nonlinear, but it's perfectly causal. Okay, so this is just to convince you that these things are different, although certainly related. All right, conclusion. So there's a lot more I could say, but won't. There's a nice relationship to this coarse graining in the fundamental description and the simple entropy, which kind of tells you what entropy did Hawking actually compute, or would he have computed if he computed an entropy. There's a relation to the Python's lunch proposal. Sorry, I somehow mangled the spelling of this. You should exchange the RA and the BI. Sorry, Hrant, if you're watching this. Talk about big black holes in ADS, multiple black holes, CR equals EPR, ghost operators, and pseudo-randomness. Generic states, as far as we can tell, these still plausibly have firewalls. We haven't gotten rid of that for generic states, but we're consistent with this observation of Lenny that if they do have firewalls, they're quickly removed by almost any perturbation. So there's a lot more to think about. What does it mean for cosmology? But I'm certainly out of time, so I'll stop. Thank you for listening.
Questions?
Nice talk, Daniel. I have a question about your picture here, back here.
Oh, there you are. Hi, Kumran.
You had many of these states which map to zero on the other side, and
yes.
the interior state.
Yeah.
There has been proposals in the past where the theory near the black hole singularity is a topological field theory. So the degrees of freedom that would be there would be, basically all of them would be equivalent, a lot of them. There would be no dynamics in the position.
Yeah.
Do you see your null state as being something you mod out by, like in topological theory, that you should not be counting as physical state inside? Or how do you think about it?
Yeah, so some people have wanted to say that these null states should have a gauge interpretation. And as I said, the idea of the null states goes back before us, right? And so there are people, for example, Meroff and Maxfield, who have said maybe there's a gauge symmetry. That isn't so natural for us because, we really want to say that there, at least for the sub-exponential states, there is a fixed interpretation. There's a unique interpretation in terms of the boundary theory. If we imagined a symmetry that totally messed up the description of the state in the effective description, then I wouldn't want to call that a symmetry because I think there is a preferred description. So we couldn't find an obvious way to make contact with that, but there may be a less obvious way to do it, yeah.
Could you elaborate on the statement that the measurement theory is nonlinear?
Oh, yeah. Okay, let me go back to that. So if we want to, that discussion was here, right? So the way it works is the kind of reconstruction we use is something that was introduced by Akers and Pennington, and it's called state-specific unitary reconstruction. So the idea is that for any given state and given unitary, they both have to be sub-exponential in the effective description, then I can find a unitary in the fundamental description which acts in the same way on the encoded state, okay? So when you do measurement theory, you introduce an apparatus and you have a unitary that writes the result of the measurement onto the apparatus, and then the idea is to take the unitary which does that in the effective description and reconstruct it as a unitary in the fundamental description. So that gives you a set of calculations you can do in the fundamental description that tell you the measurement outcome probabilities and which states you project onto. But the U, which implements it, depends on the state you start in. So that's nonlinear. Yeah, the effective description, quantum mechanics in the effective description is fine. There's no violation of that. Yeah.
Any follow-up? Are you good?
No quick follow-up.
I agree it's a little bit disturbing that, I agree it's a little bit disturbing, but it seems to be that there's just this price that we have to pay to do this, and it seems to work well enough that currently I'm in the state of being willing to pay it.
So I did call on one up here already, but that's going to be the last one. Sorry, Neil.
So you mentioned in your paper that your model does not include Lorentz invariance, diffeomorphism invariance, interactions between left and right movers, and even the dimensionality of space-time.
Yes, that's correct.
So,
I wrote that sentence.
I mean, how can you describe quantum gravity without gravity?
Well, so this is why I used words like models and analog when I was describing what we've done, right? I can only say that, in quantum gravity, we're always doing toy models, right? I mean, ADS-CFT is also a toy model because the cosmological constant has the wrong sign. With tensor networks are toy models, SYK is a toy model. Everything we do is toy models. The only thing I can say is that I feel like, when you make a toy model, the question is, have you captured the part of the story which is essential for the problem that you're trying to solve? And here I believe that the answer is yes, okay? Because we have the basic tension between Hawking's three things, okay? And we're able to see how you need to modify Hawking's assumption to avoid the tension. Now, of course, it would be better if we could solve all the problems at once, right? We do have some words in the conclusion about how one might try to figure out what this map V is, say for n equals 4 super Yang-Mills, right? But even if we do that, then someone will say, okay, but we don't live in ADS, right? So it's kind of whack-a-mole. But on some level I agree, right? We should try to realize this in more realistic things. Eventually we should do it in cosmology, right?
Well, let's thank Daniel.
Sorry. Before you guys head out, I have a quick announcement, please. For those of you who want to sign onto EduRoam, sorry, thank you. For those of you who want to sign onto EduRoam, if you're having problems, remember to forget the network and then rejoin it. So don't just put your new names in, just forget the network and then join in. And for those of you who want to put up posters, please do so right now during this break. And we have a suitcase over there. Does that belong to anybody? Okay. And finally, Orintio, can you come find me, please? I have a ticket for you. Okay, thank you.